Hello everyone, and welcome back to a new video in programming the finite element method using MATLAB. In this video, we are going to finally go along and leave the equivalent nodal loads behind and start something called the apply boundary condition. Remember, we are solving the structure and we finished the apply loads in solving the structure, and we are now going to go to the apply boundary conditions. Why? Because if you remember, we finished the apply loads and now we are in apply the boundary conditions. The apply loads took us a ton of time, but I think now we survived. So basically the worst is behind, and now the programming is going to be a little bit simpler. Now before I start applying the boundary conditions, I want to give the quick mandatory reminders. First of all, this video is part of two video series, one about theory and programming, and one about the programming alone. Both are linked on the top right. Furthermore, my dear channel members have access to the entire source code. However, if you are not a channel member, then don't worry, because every single line of code is written in front of you. You can write along and you would have the exact same code as mine. So with that being said, let's dive into the video. So sit back, relax, and enjoy the show. Now before I start, I need to give you a quick rundown of what we are planning to do when we apply the boundary conditions. In the book, Daniel L. Logan, which I explained in my Theory Finite Element series, he talks about the application of boundary series. In chapter 2, by the way, he basically explains to you that we need to partition the global equilibrium equations to boundary conditioned and non-boundary conditions. So we need to find K11, K12, K21, K22, and so on, based on if a certain degree of freedom is boundary conditioned or not. So now we need to do this here. So the apply boundary condition not only will just apply the boundary condition, but it actually will subdivide the matrix into the four pieces that it needs to be in order for us to solve it. And you can double check equation 2.5.13 in Daniel L. Logan's book, page 42, chapter 2, to check out those equations I'm talking about. Here, I'm going to first of all declare DOF equals 6. And now I'm also going to declare the number of load cases. That's going to equal the object, which is the controller, .str load cases. I think it's called like that. Now, I cannot say .count. We're not in C#. So I can call length. And now I also need the total nodes. So total nodes in this case equals the length of object.fem nodes. Remember, fem nodes are the real ones that carry the degrees of freedom. Since I have boundary conditions, I must find a storage system to store the boundary conditions. So let's go to the storage and let's give us here a storage for the boundary condition. I think I should store it here. I'll call it simply BC. Simple enough. So BC is a vector that stores the boundary conditions. So let's go there and store it. And by the way, you could program boundary conditions of Newman and of Dirichlet, meaning displacement and or force boundary conditions. I just use the boundary conditions in the typical sense, where I apply a pin and the displacement is 0. Initialize my boundary condition, so I'll go for object.bc. Does it exist? B, C, yeah. This equals ones of the size. And the size here is going to be just the length. Let's make it a column vector. So it's going to be the size of total nodes multiplied by degrees of freedom. Number of columns is 1. And this gets multiplied by NaN, not a number. So we're going to declare the boundary conditions as a vector of non-numbers. Why we declare it as the vector of non-numbers? This will come into the play very soon. Let me show you the command here in action. If I say once 10, let me just repeat this without a semicolon, you get 10 nans. I'm not initializing it to 0 because 0 boundary condition means it's held in place. So I need a way of differentiating between the meaning held in place and the meaning no boundary condition. So if I see NaN, this means that no boundary condition has been assigned to that degree of freedom. If I see anything else rather than NaN, this means that the boundary condition has been assigned with a certain displacement. Could be 0, could not be 0. Of course, in our implementation, it's going to be 0. So now we need to start marking the boundary conditions, and we also need to keep track of how many boundary conditions I have, because the K11 and K12 sizes depend on the number of boundary conditions and non-boundary conditions. The number of boundary conditions for now is 0 because we want to count them. And now I need to go for a for loop that loops from I equals 1 to the length of object.fem nodes, meaning I'm going to loop through all the fem nodes and check if the fem node is a support node and what kind of support it has. So let's fish out the node first of all. The node here equals object.femNodes of I. So we're fishing it out. And now we're going to ask the question, if node dot is support node. You see why we were marking the fem nodes back then? Now it made sense for us to mark the fem nodes back then, but now we're going to see exactly why we need it. That's the question. Now if that's a support node, then we need to know exactly what kind of support it has. Now the support is not stored in the fem node. As a matter of fact, the fem node doesn't store the type of support, but the str node stores the support. Let me show you. The str node, if I open it, does store the support. And that's the reason, yet again, why we tell the fem node to know its corresponding str node. So what I will be doing is I will go here and first of all call master fem node, because the support node is always a slave node. So now I'm going to call in for its master fem node. That's the first thing. And the second thing is I'm going to call in the master str node, because I will call in the master fem node and go to its corresponding str node. Since I have the master str node, I can get or fish out the support. I will say here support equals master str node dot support. And now I can start marking the boundary conditions and counting them. Let's go to str support and see what we did with the support. So let me think. If it is free, it doesn't count. But if it is not free, then it counts, right? So let me open the support and remember what I'm doing. We close those things and go to the support and see exactly what we have done. It's been ages since I accessed that, so let's check it out. Okay, so in the support, we are defining KUX and so on. Those, if they are equal, yeah, see, that's exactly the condition. This is exactly the conditions. I copy this. Those are exactly the conditions I need. Because if it's free, then it's not a support. So I copy this, paste it here, and change stuff. A lot of things to change, by the way. If support.kux equals str support.ku3, I'm only taking action if it's supported. So yeah, that's the condition. I'll copy. I think I don't need any of those. I paste here this 6 times for every degree of freedom and do it. So this is KUY, and that's KUZ, that's KRX, RY, and RZ. But of course here in the RZ, I need to compare with KR free, because I have a rotational free stiffness and a translational free stiffness. The rest I can delete. That's just for helping. I can just delete it here. I don't need it. And let's see what happens if I have a support. If I have the support, 2 things happens. 1, mark the boundary conditions. So here, I'll go to object dot boundary condition, and I need to mark something here. Let's say node ID is 2 or 1. Let's say this means that the first degree of freedom in X is going to be 1, and the last degree of freedom is going to be 6. What's the equation to do that? I think I know it. It's going to be node dot ID minus 1 multiplied by degrees of freedom. Yeah, I think that makes sense. Plus 1 plus 0. I will tell you why the 0 is here in a moment. This should be the degree of freedom of that thing. Now I'll mark it to be 0, because for now, the only way I have in supports is to have a 0 displacement. I could have, which is basically one time of the Dirichlet versus Newman things. I could change it to have something, a value here for the displacements, but I rather not. You can expand it yourself if you want. So we are assigning a 0 here. Now also, for the number of boundary conditions, it decreases by 1, because we're counting that. So I copy this entire thing and paste it here. And for that one, this is the I, this is the next degree of freedom. And for that one, that's the next degree of freedom, and so on. I just switch 1 extra degree of freedom and keep counting the number of degrees of freedom that are boundary conditions. So now I marked the number of degrees of freedom, and I marked the degrees of freedom that are conditioned by the BC. So we finished marking all the nodes. Now, since I marked everything, I'm gonna go here and declare number non-boundary conditions for now. Let's just equal for 0 for now. I'll change it. It's gonna equal the total nodes multiplied by the degree of freedoms. Those are all the degree of freedoms, minus the degree of freedoms that have been boundary conditions, non-BC. Why? Because this will control the size of K11, K22, and so on. Now here, I will have a counter, and this is basically a counter for filling. This is a filling algorithm. I will just try to keep it as simple as possible. Row K11 is going to equal 1. Row column, this is a filling algorithm, and those things keep track of the current column we are in when you fill in something. Row K12 equals 1. Row column K12 equals 1. I'm initializing those things. We start our initialization schemes. There is a ton of things I need to initialize, and those need to be stored in the controller here. So besides those things, I need to store F1, and this is about the equation of the finite element method. Remember, we need to subdivide our K matrix into 4 matrices, our D matrix into 2 matrices, and our F matrix into 2 matrices. So F1, F2 are needed as matrices. We need to initialize them. D1 and D2 are needed. K11, K12, K21, and K22. All those matrices are necessary for solving the finite element problem. So now here we need to initialize those things. So let's start initializing. Object.f1 doesn't exist. F1. This equals zeros of the number non-boundary conditions. That's where we're counting them. And number load cases. Furthermore, object.f2, this is going to be zeros initialization, but this is for number BC and number load cases. So this initialized all the matrices. Now we need to fill the matrices. How do we fill the matrices? We need to run in a for loop again. This time we're going to run for a for loop that goes through all the degrees of freedom. So from I equals 1 all the way to the total nodes multiplied by the degrees of freedom. We are running through every single one of those degrees of freedom. Now we're going to ask the question, is it a boundary condition or not? How do I know if it's a boundary condition or not? Well, that's the reason why I marked them here. Remember when it was NaN, and any boundary condition has been marked by as 0. Now here the question is very simple. If it is an NaN, it is not a boundary condition. If it's not an NaN, then it is a boundary condition. So let me try. Does it work even? Let's say x equals NaN. Now x double equals NaN. Does it even work? Because we need the logical check. Wait. So x equals 5 or 6, whatever. And now we say, does x equal 5? The answer is 1. That's true, because yes, x equals 5. Now if I say x equals NaN, it stores the value. But when I say x double equals NaN, I'm asking, is it equal to NaN? It says me no. So there must be another check. Let me just check very quickly in MATLAB. I think it's called is NaN. Let me see. Is NaN? Okay, it works. So it's called is NaN. Interesting. So for an NaN value, I cannot simply say x double equals NaN because it destroys itself. But I can ask the question, is NaN for the x, and it will answer correctly. Now if x equals 5 and I ask the question, is NaN x, it should give me a 0. Fantastic, it works. So here the question is NaN what? The object.boundary condition at the degree of freedom I. So if that is NaN, then we have found. So wait, if it's NaN, then there is no boundary condition. So here I write no boundary condition. And if there is no boundary condition, then it will have a force in F1 and the displacement in D1. We're basically filling F1 and D1 here. in F1 and D1, okay? So how do I do that? Well, let's do it the following. Dot F1, because not a boundary condition, equals, I'm missing something, because this should include the global loads and the equivalent nodal loads. We have calculated the equivalent nodal loads, but we haven't added them together. That's a to-do. Let me just put here, to-do. Check if we added the equivalent nodal load to the global load. So here, let me just check if it even exists. Global. Yeah, there it is. And there it is. I think I didn't add them together. This could prove dangerous later. I need to double check that. For now, let me just continue my task here. I don't want to change my focus. So this here, F1 of what? I have multiple load cases, right? So it doesn't work like that. I must cycle through the load cases. For J equals from 1 to the length of object.str load cases. I must cycle through load cases because it's a matrix, not a vector. I don't think I need to cycle through it. I could just use vector operations. It might be easier for readability, but I could just put double colons here and took the entire row. I'd keep it like this. Maybe it's easier for readability. Yeah, I'll just keep it like this because of readability issues. So here, object.f1, where at the degree of freedom I and the load case j, this is gonna, wait a minute. It's not at the degree of freedom I, because we are filling it in and we're counting exactly. So this is not at degree of freedom I. It is at row f1, where we are standing, and j, and that is going to equal to the object.global load matrix. Does it exist? Yeah, it exists. And this is I and j. Yep, that's the case. Now, I'm still worried about this, but for now, let's continue. And control paste here, D1 and D1. Now, since we used it, when we finish here and we go to the next degree of freedom, we need to increment. So row F1 equals the row F1 old plus 1, and row D1 equals the row D1 plus 1. So we're incrementing because we're going to fill the next value once it happens. Now, this happens if it is not a boundary condition. Now, what happens in the else condition? Because here we have an if statement that says no boundary condition. However, otherwise, it is a boundary condition. So now we can do the same thing here, the exact same thing, with one difference. The difference being that now I'm filling F2 and D2 because it is a boundary condition. So this becomes F2 and D2. I'm extremely worried about this in the equivalent nodal load. It's like a looming threat in my mind now. Okay, so we established F1 and D1. We can just close it here and continue by filling in the harder part, which is all the matrices of K11, K12, and so on. So here I will go for and say filling in K11, K12, K21, K22. Okay, I know what you're thinking. You don't need to fill K21 because they are symmetric, and you are right, but I'll just fill it anyway. So now this is a square matrix, so I need to run two loops. One for the degrees of freedom in the rows, and one for the degrees of freedom in the columns. So for I equals from 1 to, I still haven't checked. I still haven't checked my code. I am predicting a ton of errors. But that's for future me to worry about. Let's be happy now. For j equals from 1 to total nodes multiplied by degrees of freedom, and is the row a degree of freedom. So here, there will be an if statement. So I'll copy this if statement. I think I removed it, right? So if is none, object.boundary condition of I. So if that is an NaN, this means that our row is a degree of freedom. And if that's the case, our row is a degree of freedom. If that's not the case, then our, is not a boundary condition, is not a boundary condition. And if that's not the case, then our row is a boundary condition. But that's not enough, because K11 meets two conditions. K11 has rows, non-boundary conditions, and columns, non-boundary conditions. K12 has rows, non-boundary conditions, but column, boundary conditions. K21 has rows, boundary conditions, but columns, non-boundary conditions. And K22 has rows, boundary conditions, and columns, boundary conditions, both. So it's going to be a little bit of a headache. You could figure it out yourself, or you could write along. I think we finished application of boundary conditions by subdividing our matrices and our forces and our displacements into multiple pieces. And I think we're done. We will debug later, but for now I can say, yeah, that's everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give a boundary condition sized shout out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support to the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing, because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel. I will catch you in the next video. Bye bye.